Hey, folks. I hope y'all had a fantastic break. Um, what we're going to do today is kind of review some of the things we talked about just before break, and then um, talk a little bit about the final exam. That's what we'll do today. So, reviewing what we did last time, we talked about the integers mod n. It's the set of equivalence classes of integers using this equivalence relation. It's this. We write this z mod n with like a little subscript of an n. So a couple of things I want to review here from this slide is what we mean by an equivalence relation. An equivalence relation is a relation that is reflexive, symmetric, and transitive. So the idea is that reflexive is a single, operates on a single element, that x is always congruent to itself, that x minus x is equal to 0, and n always divides 0 because 0 is equal to n times 0. That x is equivalent to y if and only if y is equivalent to x. That is, the order should not matter. Y minus x would be some value, but x minus y would be the negative of that value. And if n divides the positive value, then n divides the negative value as well. That's the idea. And then the transitive property involves three elements. It says that if x is equivalent to y and y is equivalent to z, then x has to be equivalent to z also. That is, if two of them are equivalent, if they're equivalent in pairs, then the third one has to be equivalent also. So if x and y are equivalent and y and z are equivalent, then x and z also have to be equivalent. Formally, equivalence classes are notated with square brackets, but in practice, we attempt not to write the square brackets unless we have to make a distinction between equivalence classes and numbers. So when we write this bracket around, say, 4, and we're in Z mod 5, we're talking about the set that contains 4, but it contains everything else that's also equivalent to 4 mod 5. So that would include 4 plus 5 is 9, and 14, and 19, and 24. And then working backwards would be negative 1, negative 6, negative 11, and so on and so forth. That this 4 stands for an entire set of possibilities, but all of these possibilities, when I divide them by 5, leaves a remainder of 4. Okay. So we've studied this definition before with integers, and what we're now dealing with is integer classes. And it's a subtle difference, and it's a difference that sometimes doesn't make much difference at all, but I want to talk about it for a moment. So if we're just looking at the integers, I look at this equation, this congruence, 3n plus 5 is equivalent to 4 mod 7. N equals 2 is the solution because the left side, 3 times 2 is 6. 6 plus 5 is 11. And the right side is the number 4. 4 minus 11 is negative 7, and that's divisible by 7. I'm looking at a number on the left and a number on the right, and the difference between those numbers is a multiple of 7. If I'm looking in the set not of the entire integers, but the set of equivalence classes. N equals 2, which is really the congruence class 2, is a solution to the congruence, because the left side, 3 times 2 plus 5, is the set containing 11, and the right side is a set containing 4, and this set and this set are the same. That this is a statement about two numbers. This is a statement about two sets. And like I said, the calculations work out the same in both cases, but the objects that they're talking about are different. Okay? If we're working in Z mod n for any positive integer greater than 1, and we have A, B, C, and D are equivalence classes, where A and C are equivalent and B and D are equivalent, then we can add equivalent classes and get the same result. So A plus B, it would be the same as C plus D. We can multiply equivalent classes and get the same result. If we want to subtract, we have to add the negative of the equivalence class, the additive inverse of the equivalence classes, and those are the same. And if I'm raising to a positive power, these are the same also. What happens if we raise to a negative power, though? Well, then we run into a problem. And the problem is that A to a negative power would be like 1 over an equivalence class to a positive power, but we don't know how to take 1 over a set. But 1 over a set is undefined. And even if we look at the numbers in the set, the 1 over an integer may not be an integer. And 1 over an integer may not be an integer. So if we're dividing 1 by the set, dividing by the set is undefined. And if we even were dividing by the numbers in the set, the numbers in the set may not be something we can divide by 1. So we can't define this for m less than 0. We can only define this for m greater than 0. Okay? But all of these are true facts, and you can reference them without having to cite them. But because division is not defined in Z mod n, we have to rely on multiplicative inverses when they exist. We'll solve this congruence by adding negative b to both sides of the congruence, and then using what we talked about last time, the equivalent, the extended Euclidean algorithm, to find an inverse for A, and then multiplying both sides of the congruence by that inverse. And so what we'll do here is work through a couple of examples of finding multiplicative inverses. So I want to solve this congruence mod 11. So the first thing we're going to do is we're going to take this 6 and this 11 and perform the equivalent Euclidean algorithm on 6 and 11. So I'll divide 6 into 11, and that goes 1 time with 5 left over. And then I take these two numbers on the outside, and I keep going, but this time I'm going to divide 5 into 6. And that goes 1 time with 1 left over. And again, I'll take the two numbers on the, the number at the beginning and the number at the end of this chain here, and divide that. 1 goes into 5 times with 0 left over. The last non-zero remainder we got is the GCD, and it must equal 1. Otherwise, there will not be a multiplicative inverse. So it must equal 1 to have an inverse. And then to find the inverse, we do what's called the extended Euclidean algorithm. And we'll start out by placing a 0 out to the side and then a 1 over here. And what we'll do is we will subtract 0 minus this product, 1 times 1. So 0 minus 1 times 1 is negative 1. And then I will do 1 minus this product. So 1 minus negative 1 times 1 is 1 plus 1, which is 2. And the last number we get up here is the multiplicative inverse. So now that we have the multiplicative inverse, let's put it to use. The first thing I'm going to do is I'm going to add negative 3 to both sides. 6x plus 3 plus negative 3 is congruent to 8 plus negative 3. And so 6x is congruent to 5. And now I'm going to multiply both sides by the inverse. 2 times 6x is congruent to 2 times 5. So 12x is congruent to 10. 12 and 1 are congruent mod 11. So I can replace a 12 with a 1. That's this statement here, statement number 2. I don't know where I have it in my pen. There it is. That if A and C are equivalent, then I can substitute A for C, or I could substitute B for D. In this case, I'm substituting 1 for 12 because 12 and 1 are equivalent mod 11. And I'm allowed to do that. And so this is my solution. X is equal to 10. X is congruent to 10. We could check that. Is 63 congruent to 8? Well, 8 minus 63 is negative 55, and that is divisible by 11. And so that checks. Okay. We perform the Euclidean algorithm to make sure that the GCD is equal to 1. Then once we've made sure that GCD is equal to 1, we perform the extended Euclidean algorithm to get the multiplicative inverse. And then we use the multiplicative inverse to solve the congruence. And for small numbers like 11, you could kind of figure this out in your head. You probably could just go through brute force and check a bunch of numbers until you found one that worked. But for larger numbers, like this one here, you don't want to sit here doing brute force all day. You want to be able to solve this congruence using the Euclidean algorithm. So let's try this one. I'm going to use these two numbers, 103 and 163, to start out. So 103 goes into 163 one time. And that leaves me with 60 left over. 60 goes into 103 one time with 43 left over. 43 goes into 60 one time with 17 left over. 17 goes into 43 twice with 9 left over. 9 goes into 17 once with 8 left over. 8 goes into 9 once with 1 left over. And finally, 1 goes into 8 times with 0 left over. And the last number before the GCD, or before the 0, is the GCD. So we have a long chain here that ended in a 1. Okay? Now we'll do the extended part of the Euclidean algorithm. We start with a 0 and a 1. 0 minus this product is a negative 1. Then 1 minus this product, 1 minus negative 1 times 1 is 2. And now we'll take negative 1 minus this product. Negative 1 minus 2 times 1 is negative 1 minus 2 is negative 3. So we'll do now 2 minus this product. 2 minus negative 3 times 2 is 2 plus 6 is 8. Negative 3 minus 8 is negative 11. 8 minus negative 11 is 19. So now we're ready to solve this congruence. We have 103x plus 19 is congruent to 47. So 103x is congruent to 47 plus negative 19, which is the same thing as 103x is congruent to 28. Now I'm going to multiply both sides by 19. That's my inverse. 19 times 103 should be a multiple of 163, or it should be congruent to 1 mod 63. So this is, on the left side, we get 1957x. On the right side, we get 532. All right. But this number should be congruent to 1. And this number we can reduce mod 163. So let's do some calculating here. I have not left myself a lot of room to work, so let's try it down here. Well, I do 163 into 1957. That goes one time and leaves me with 327, and then twice 326 leaves me with a remainder of 1. And so this side is equivalent to just 1x. Well, I do 163 into 532. That goes 3 times and leaves me with 43. Is that right? 12 minus 9 is 3. That leaves me with 12 minus 8 is 4. And so x is equivalent to 43. Okay? So that's the solution to this congruence. Um, what we will look at on Wednesday is the RSA algorithm, which is a technique for encrypting data using difficult to solve congruences, essentially. And we'll talk about how that works on Wednesday. Y'all have a fantastic couple of days. I'll see you again. Okay? Take care.